Hi guys, and welcome to this lecture. So in this exercise, we're going to look at the concepts behind debugging a piece of C code. So this is quite important for all software development because we are all human and therefore software rarely works first time. The ARM Cortex-A9 processors in the Zynq 7000 devices are supplied with a very advanced debug and trace interface. But we'll simply cover some of the basic debugging techniques. We shall now create a project to show the steps required for debugging. The finished version of exercise 2 is an ideal design for this exercise. So let's go ahead and create a new software application called exercise 3 using the standard cut and paste operations based on exercise 2. If you don't have the files from exercise 2, you can download them from the link below or check out the previous video in the playlist. Okay, so moving on. So the steps to do this are intentionally not explained because it's very intuitive to do. Once you've made a new copy of the application project, experiment with changing the file name from exercise _0.2.c to exercise _03.c or lab2 to lab3 depending on what you've named it. And this will match your new project. And you might want to change the printf message inside of the file too, just to convince yourself that you are running a different version of the software. The rename feature can also be found in the right click menu. So to go ahead and debug our code on the processor, we shall use the system debugger, which is built into the SDK. And this can be accessed by right-clicking on the project name and choosing Debug As from the menu rather than Run As. So right-click on Exercise 3 or Lab 3 software project and choose Debug As. Go to Launch on Hardware System Debugger from the menu. So after a few seconds, you'll see a pop-up message asking you whether you want to switch to debug perspective. I want you to choose yes. Okay, so now the window will all rearrange themselves and you'll now be in the debug perspective rather than the C perspective. A perspective in the Eclipse SDK tool is a name given to the layout of the various panes of the screen. The layout of the screen in the SDK tool is critical to making the software engineer more productive. When writing the developing code, it is useful to have a very different layout of the screen rather than running the debugger. Different information needs to be displayed, and the required size of each pane is very different. So in the Eclipse SDK, the user can toggle back and forth between the different perspectives by using the buttons in the top right corner of the screen. Advanced users can even design and use their own perspectives to match the precise needs and personal preferences. So with the debug perspective open, you will notice that the code editing window has become smaller and has moved to the left of the screen. The Project Explorer window has vanished altogether. We no longer need to concentrate on the different applications because we're just debugging just one. In the code editing window, you'll see that there is a line of code that is highlighted in green and also marked with a blue arrow in the left margin. This is showing you that the processor has been halted at this stage of the application and the software execution is under control of the GDB debugger. The highlighted line of the code is GDB, which is telling you I am about to execute this line of code, but I have not done it yet. The pane above the code editing window shows that the exercise 3 or lab3.elf file is being debugged, and debug control is being handled by something called the TCF. For those who don't know what TCF is, it stands for Target Communication Framework System, and the utility which manages the connection between the GDB debug engine and the JTAG cable. You'll be able to see that the code is halted inside the main function. This display will update and show you when you're inside the function, and the hierarchy will be shown to demonstrate which functions call each other as you step through the code. To see a practical example of this, we'll step through our code until we descend into the init_platform function. At the top of the debug pane, you'll see a series of new icons. There is a green resume arrow, which tells the code to continue to the next breakpoint. More on breakpoints in a moment. The red square means terminate or to halt. And there's a series of yellow arrows which control the single stepping of your application. So hover your mouse over to the yellow single step arrow buttons and locate one marked stepped into. Click this button, perhaps a few times depending on your code that you have copied from exercise 2. And you will step into the init_platform function. Observe what happens in the debug pane when you descend into the function. You will start to see this _start function underneath the main function, which is also underneath the init platform function. This will tell you that the start has called main, which in turn has called init_platform, and therefore tells you which function you have passed through on your way to the current pointer of your code. In our example, it's very simple, but in a very complex application, it can be very useful to see how you got to your breakpoint. We'll now examine the difference between step into and step over buttons. So inside the init platform, there is a further function called enable caches. Click step into again, and you'll see that the debugger will descend once again into this function. Notice that the change to the debug pane and the hierarchy view. We can now single step through the low level function if we wanted to. And let's imagine that we wanted to execute the end of the function and return to just the one level of hierarchy up. So go ahead and click the step return button, and the code will execute all the way through the current function and back all the way up to the level above. Now click the step over button, and now you'll see the debugger stays at the same level of hierarchy, but executes all of the init UART functions in one go. Click step return to get back to the main function. So in the code editing pane, scroll down a few lines and find the line of code which sets the direction of the GPIO port. In the blue margin to the left of this line, double click your mouse and you'll see a blue dot with a tick marker appear. This is a breakpoint and tells GDB that you wish to always stop at this point. Now click the green arrow resume button, and the debugger will execute all of your code between the current position and the breakpoint that you have just set. This is a useful way to execute a lot of your application, but only stop at the section you wish to debug. Okay, so at this stage, we'll turn our attention to the variables pane, which you'll see in the top right corner of the screen. You'll see all of your local variables, which are relative to this function. It's a simple application, so you should only see 3 or 4 listed. One of the variables is status, and hopefully the value will be 0. This proves that the xGPIO CFG initialize function completed and returned no errors. This is great news. So in the variables pane, you should also see the GPIO config placeholder, which you created in exercise 2. Recall that this is actually a struct, which is a collection of variables under one name. To learn more about structs, please check my other video that I'll have the link below. Okay, so expand the hierarchy of the GPIO config struct by clicking on the white arrow in the left of the name. You will now see the 2 variables contained within the struct and their values. The GPIO config base address variable probably seems to be a meaningless number, but that's because we are looking at the decimal number rather than a hexadecimal value. A second column exists in the variables table, which shows the hexadecimal equivalent of the number. Now the number should make more sense. This is the base address of the GPIO in the Zynq 7000 memory map. You can also expand the myGPIO instance of the variables pane. You'll see that it's actually a struct containing another struct, and therefore there will be multiple levels of hierarchy that you can explore. You may want to see that some of the variables are highlighted in yellow. This occurs when the variable has updated since the last breakpoint during the last single step operation. This feature of the debugger can be very useful because it draws your attention to things that change during your debugging session. But the variables pane is not the only place where you can explore the value of the variables. In the code editing window, hover your mouse over the name of the variable or struct. A pop-up helper will display that will give you the same information. Simple but useful. Okay, so now add another breakpoint inside the for loop or the for delay loop, which prints the dot characters to the UART. Click the resume button and the code will advance to the inside of the loop. Click resume a few more times and observe the change to the variables, which counts the iterations of this loop. You'll see the variables incrementing with each click of the resume. Single stepping our way out of the loop can be very tedious and would require 2000 mouse clicks. But what if there was a fault in the code and that was just right before the last iteration of the loop? What would you do? Well, the debugger can help us in this case as well, because we can dynamically change the values of the variables in the middle of executing the code. So inside the variables pane, click on the value of your loop variable and manually change it to 1997. Now click the resume button and notice a few clicks we have left the loop. So if you find yourself back in the loop but with the loop variable set to 0, it's because you have exited the loop and re-entered it on the next iteration of the next application. By using this feature, we have manually updated the value of the variable and set it to a specific condition in the software. This can be used to debug a known set of events which might be causing problems in your application. Okay, so that is it. You have just mastered the basics of single-step debugging. So feel free to play around in the debugger to familiarize yourself with the features that are available. And if you want to be challenged, I have a end of exercise challenge. It is sometimes convenient to temporarily disable the breakpoint, but still remember where you put it. The SDK will allow you to do this. Select Breakpoints tab in the top right corner of the screen, and you'll see a list of breakpoints that are currently set up. So you can experiment with the tick boxes to the left of the breakpoints and set up the breakpoints in your code and then enable and disable them to see how the debugger works. Okay, so that is it for this lecture. In the next lecture, we're going to go on to expanding your design into the programmable logic in Vivado. Okay, hope you enjoyed this lecture. If you enjoyed this lecture, please give me a thumbs up or like this video, and I'll see you in the next class.